Hello students. How many ways can we get a 5 on 2 dice? So, let's say I have a red die and a green die, and green die, and I want to get a total of 5. Okay, well, I have 4 choices for what I can roll on the red die, 4 choices for what number I can place on the top. It doesn't matter if I roll them or if I'm just moving them around and placing the number I want on the top. So, why do I only have 4 choices? Well, because I can't start with 5, otherwise I'll be in trouble. And since there's no -1 on my die, on the second die, hopefully, I know I can't roll a 6 as well, or I can't have a 6 as well. So I have 4 choices for red. But then, for green, I'm only going to have 1 choice. No matter what I chose for my red, I'm only going to have 1 choice for the green, because the green is going to have to make it add up to 5. So if I have a 1, I have to have a 4. If I have a 2, I have to have a 3, a 3, a 2, a 4, a 1. Now you might say, okay, do we need this distinction about the red and green in order to calculate the number of ways? And now we do have to talk a little bit about real life. See, in real life, even though, if we're calculating probabilities, even though the 2 dice might look the same to us, the dice are not actually the same, right? They're no dice are actually the same, right? They're not going to be perfectly identical, and they're not really the same one. Even if they were perfectly identical, still one of them would have rolled one number and another one of them would have rolled another. Okay? So in terms of probability, I don't want to break this down into the 2 cases of 1 plus 4 and 2 plus 3. If I say, hey, I want indistinguishable, completely indistinguishable situations, how many ways can you roll a 5? You might say, hey, well, you can either get a 1 and a 4 or a 2 and a 3. And that's one way of thinking about it. In terms of probability, though, we do want to take into account which die rolled which number, meaning that we have 36 different possibilities for all the things we could roll, 6 on one die and 6 on the other, whether or not I can tell them apart. And I know I have 4 times 1 ways of rolling a 5, and in probability what we can do is we can then just say, oh, I have 4 out of 36, a 4 in 36 chance of rolling that 5, so that's what, 2 in 18, or 1/9 is our probability. So you could say, hey, the odds of rolling a 5 on 2 dice are 1/9. But we're not going to go in the probability direction. I just wanted to point out that if you can count, you can do probability. So what direction do I want to go into? Well, let's talk chess. Suppose I have, and let's make the board small. I could make it large, but that would be a lot of drawing. Let's say I want to place 3 rooks, and they can't attack each other. So I want to place 3 non-attacking rooks on the board. Okay, well, I know that I can't have 2 rooks. Oh, by the way, rooks can move as far as they want, either horizontally or vertically. So, I know I can't have 2 rooks in the same row, and I know I can't have 2 rooks in the same column. So let's think in either terms of rows or columns. It actually doesn't matter which. Suppose I want to look at the first row. Well, you could say, hey, in the first row, I'm going to have 3 different possibilities for where I can place that rook. And then, in the second row, I'm going to have to place a rook in the second row because I can't put the other 2 both in the last row. I'm going to have 2 possibilities for where I can place the next rook. And then, no matter where I've placed them, there's still going to be 1 place for me to place a rook in the bottom, because if I take up a column and I take up a column, there's going to be 1 column that's still free in the 3rd row. So I have 3 times 2 times 1, or 3 factorial, or 6 different possibilities for how I can place 3 non-attacking rooks on a 3x3 chessboard. Okay. Not so bad. Yes, it generalizes all the way to the 8x8. You're going to have to put 1 in each row and 1 in each column. And well, you'll get 8 choices for where you place the rook in the first row and 7 for the next, and so on. Okay, let's make it a little harder. Let's try to place 2 non-attacking queens. Okay, well, now it's a harder question. What do queens do? How do they move? Well, they can move as far as they want, horizontally, vertically, or diagonally. Okay. And there are many bad ways you could look at this. In terms of using the product rule, there are many bad ways we could look at this. But one thing to notice is that I don't want a queen in the middle. I can't put a queen in the middle, right? No way I can put the queen there. Otherwise, it would attack everything. So you might say, okay, well, wouldn't it matter? Like, there's a nice symmetry here. You could rotate or flip the board. You might say, wouldn't it matter whether I try to place a queen in a diagonal slot or a slot that's sort of on the edge and not on the diagonal? And the answer is yes. I mean, we'll call them corner and edges, right? Yes, that's true, but let's try to think about this. I can't have both queens on the corners because each corner attacks every other corner. And I can't have both queens on the edges because each edge attacks every other edge. So once I realize that, I think, hey, I have to have one corner queen and one edge queen. So now, instead of going like piece by piece on the board, or I should say square by square on the board, and trying to ask myself what goes there, I'm going to say, okay, I have one corner queen and one edge, corners and edges, one edge queen. Okay, so how many choices do I have for the corner queen? Well, the corner queen is going to have 4 different possibilities because there's 4 corners. And then no matter what corner queen, where corner queen is, how many possibilities am I going to have for the edge queen? Well, if I'm in this corner, I have these 2 edges. If I'm in this corner, I have these 2 edges, this corner, these 2 edges, and this corner, these 2 edges. So I'm always going to have 2 possibilities for the edge queen. That gives me a total of 8. So you can't just necessarily jump into these problems and expect the product rule to work on the first try. Sometimes you have to think about the way of setting it up. But I see that, hey, I have 4 possibilities for my corner queen, and then no matter where that queen is, I'm going to always have 2 possibilities for the other. Or I could have placed the edge queen first, and then I would have had 4 different possibilities for that. And I would have said, okay, well, wherever that edge queen is, I'm going to have 2 possibilities for the corner because it would have been these 2. I can't have them adjacent to each other. So those are some more examples of the product rule with dice and chess. What else do we have in games? Cards. But with cards, we do have to be careful. Like, you might think at first that it would be easy to just use the product rule in order to determine the number of hands that are, say, a flush. That means all of the same suit. So all hearts or all clubs, right? And I might want to even set, let's say we're playing 5 cards that we're drawing here. I might try to set them up as cards, and I might say, hey, I have ace 2 all the way through 10. That's 10 possibilities there. And then jack, king, queen. So I have 13 choices, let's say. I'm going to have 4 choices for what my suit is. And then you might say, hey, I have 13 choices for the first card, 12 for the next, 11 for the next, and so on. But this does not work. This fails. Because let's say you choose club, and then you choose ace, 2, 5, 7, 9. Well, you've counted that as your possibilities for a hand. But in your hand, you don't care which card comes first. It's just a set. It's just a collection. So that would be the same as ace, 7, 5. I don't even have to put the ace on the left. 9, 2. So we're going to need to be more careful before we start counting hands of cards. But those are some examples in this video involving games.